Hi guys, it's your date with the magnetic dipole. A small current carrying coil is a magnetic dipole. I've already posted a video on the electric dipole. On parallel lines, we are going to now analyze, study all the properties of a magnetic dipole. So here you are. A small current carrying coil is a magnetic dipole. If a coil whose plane is in the YZ plane and the axis of the coil is along x-axis, I'm taking the usual right-handed Cartesian. This is x, this is y, then this is z, circle dot. So plane of the coil is in the YZ plane, and if you view it from here, the current flowing in the coil is anti-clockwise when seen from here. Then this face of the coil facing the eye, this is a north pole, and the back one is a south pole. The coil as if is like a bar magnet, So this is equivalent to a bar magnet with this as the south pole and this as the north pole. By the way, for a magnet, the south pole is taken as a imaginary negative magnetic charge and the north pole is a positive magnetic charge. The SI unit of the magnetic charge is ampere meter. Ampere meter. And that exactly is the unit of the pole strength of a bar magnet. Pole strength of a bar magnet. Now, if I break this coil or understand this coil rather as a short bar magnet, and this bar magnet is a magnetic dipole, then all the properties of the magnetic dipole I can link up with the current carrying coil as well. In fact, current carrying coil is a magnetic dipole. If that is so, then this is the axis, this is the axis of the dipole, and this is the equator. Once again, my usual style of teaching physics, symmetrical approach, parallel approach. So whatever is your knowledge that you have acquired on electric dipole, why don't you use it in understanding the behavior of the magnetic dipole? So here you are. The magnetic field at the center of the coil, if it carries current I, you all know that, we have done that in the earlier part of the chapter, that is mu naught I by 2R. And the direction of the field at the center, well, the right hand grip rule, that is along I cap, axis of the coil. The magnetic field at a point P on the axis of the coil, we have proved that making use of the Biot-Savitz's law, mu naught I by 2 R square upon x square plus R square to the power 3 by 2. And the direction once again is I cap. Mind you, using the Biot-Savitz's law, if I ask you to find the magnetic field at any off point, off axis point, for example Q, for example S, you'll put your hands up. Sorry sir, we can't do it. Yes, you can't do it. But then, here I teach you the parallel technique by what I taught you in my video on the electric dipole, which had electric dipole moment P arrow. Similarly, the magnetic dipole moment has magnetic dipole moment small m arrow. And the direction of the small m arrow is from south pole to north pole along the axis. In fact, the direction of the dipole moment is same as the direction of the axis of the direction of the magnetic field of the coil, that is along the axis, perpendicular to the plane of the coil. Well, south pole is a negative magnetic charge, north pole is a positive magnetic charge, and then the small distance between them is the dipole arm. Is the dipole arm? Well, in this case, it will be just the width of the wire in which the current is flowing. And for the electric dipole, the dipole moment is QD. So here also it will be QD, but Q here is the pole strength. So ampere meter into meter, that becomes ampere meter square. Well, that's the SI unit of the magnetic dipole moment. So here you are. If I visualize on this parallel approach the current carrying coil also has a magnetic dipole, then this has a dipole moment M arrow, just like the electric dipole moment P arrow. M arrow is Indian Airlines IA arrow. I is a scalar. A, the area of the plane is a vector. So IA arrow. So I multiplied by pi r square, r is the radius of the coil, of course, I cap. You notice the direction of M arrow is same as B arrow, same as BO arrow, same. And notice that M arrow is parallel to B arrow. That's what I've been saying. Now from the equation 2, let me show you something very interesting. From the equation 2, suppose our dipole anyway has to be something very small. So R is very small and it is much less than X. R is very small, much less than X. It's a small coil. Then in that case, you can neglect X square in this expression, X square as compared to R square. So you get the expression magnetic field at the point P is mu naught I by 2 R square upon R cube. Of course, direction is I cap. That is mu. Now I just do a small trick because I have to bring the area, and in order to have the magnetic dipole moment. So what I do, multiply and divide by pi. So I get mu naught I by 2 pi r square by x cube. Sorry, this was x cube, not r cube. There is a correction, please. This is x cube. R square is neglected as compared to x square. So below you get x cube. Now look at this expression. Now I multiply and divide by 2 because I have to bring in mu naught by 4 pi, the magnetic field constant. So mu naught by 4 pi, I pi r square is m, x cube is already there. So I get the mu naught by 4 pi 2m by x cube I cap. Mu naught by 4 pi is k dash, where k dash is mu naught by 4 pi, the magnetic field constant. Mu naught is the permeability of free space or air, values almost the same. This expression reminds you of the expression of the electric dipole moment and its electric field on the axis of the electric dipole, 2 kp by x cube. There k is 1 by 4 pi epsilon naught. So similar, 2 k dash m by x cube. Beautiful parallel analogous approach. So in general, now once I have done that, then in the electric dipole I showed to you using the polar coordinates, I can do the same. The magnetic field at Q, any general point whose position vector from O is x, then the magnetic field at P due to the dipole is k dash m by x cube into 3 cos square theta plus 1 to the power half. Same expression that we did for the electric dipole. I am reminding you again and again. And the magnetic potential, that was kp cos theta by r square. So here it is k dash m cos theta by x square. Now I can know for this dipole even the magnetic field at the equator a point S. At the point S on equator, Well, there it was Kp by x cube. Here it is K dash m by x cube. Okay, let us now try to understand the behavior of the magnetic dipole in an external uniform magnetic field. Suppose the current carrying coil or the magnetic dipole is placed in an external uniform magnetic field of strength B arrow, then just like the electric dipole, the magnetic dipole would also have magnetic potential energy. It will also experience a torque. Let us see. The magnetic potential energy possessed by the dipole within the external magnetic field of strength B arrow is minus M arrow dot B arrow. Remember, minus P arrow dot E arrow for the electric dipole. That is minus MB cos theta. Theta is the angle between the two vectors, that is M arrow and B arrow. U naught for theta equal to 0 degree state, the least magnetic potential energy state. The least magnetic potential energy state, theta 0 degree, cos theta 1, so minus MB. This is the most stable state. Call it as the equilibrium state. Well, if the dipole is disturbed and, well, it is taken to an excited state, that is the theta state, same as this, then the magnetic potential energy would be minus MB cos theta, that is an excited state, more magnetic potential energy. And in that state, just like we learned in our study of the electric dipole, the dipole would experience a torque. There it was P arrow cross E arrow. Here it is M arrow cross B arrow. So easy, so simple. Just you have to do a parallel study. So tau is MB sin theta. And what is the role of this tau? The tau will try to bring the dipole. Now I am thinking of the dipole just like a bar magnet, So if it has come like this, it will like to come to the theta equal to 0 state. But then due to inertia, it will overshoot. Then this, and like this, it will execute oscillation. Let us investigate if this oscillation is an SHM. Let's see. It will be SHM only if theta is very small. If theta is very small, then sin theta equal to theta in radians, and then the restoring torque would be MB theta. M is constant, B is constant, so it's a constant multiplied by theta. Theta is the angular displacement. I call K slash, capital K slash, as the Hooke's constant here. Value is M into B, and if that is so, then the restoring torque is proportional to theta. It is a case of angular SHM. If it is a case of angular SHM, then it has angular frequency omega, the Hooke's constant, divided by I dash. I am using I dash for the moment of inertia of the dipole, because I have been using for the current. So I dash is the moment of inertia of the dipole. So moment of inertia about this axis, because the dipole is rotating like this. Time period. So time period will be 2 pi by omega. So it is 2 pi I dash upon K slash, and K slash is MB. So I get the expression for angular frequency and time period. Now here I like to remind you something. We have this current carrying coil as a magnetic dipole. It is placed in an external magnetic field of strength B. It experiences a torque. When it experiences a torque, it will have angular acceleration. Angular acceleration will increase its angular velocity. The coil will rotate in the magnetic field. It is the case of an electric motor. So with this concept, with this idea, we can learn the working principle of electric motor. Electric motor and moving coil galvanometer, something similar, both very important for your syllabus. But both these devices, the electric motor as well as the moving coil galvanometer, I will not discuss in this particular video. I'll have a separate video for that. I'll build up a separate video and post it on YouTube. Only thing is that in the case of moving coil galvanometer, the restoring torque is going to be opposed. This restoring torque, or I can call this time now as a deflecting torque, because if it is a deflected the coil in the field, then I can have the coil suspended from a suspension fiber, and there will be a twist in the fiber, and there will be a restoring couple set up and all that principle that we will discuss in a complete video on the working principle of a moving coil galvanometer. So with this, you understand the different properties of the dipole, the field, the potential, and also the behavior of the dipole in a uniform magnetic field. Now, what if the field is not uniform? Then surely, apart from the torque, it will also have force, because on one of the pole where the field is strong, there would be a greater magnetic force, because the magnetic force once again would be Q times B. But mind you, Q here is the magnetic charge, unit ampere meter, pole strength. So in that case, the dipole while rotating will also translate. So all these ideas are going to help you a lot in understanding the behavior of the materials with the magnetic properties when they are placed in magnetic field, uniform or non-uniform. I'll now take up two problems to consolidate your understanding of the. Now, to consolidate your understanding of the magnetic dipole moment, I discussed two interesting problems with you in this video. First problem is like this. Think of this as a circular coil. Now this is a circular coil, and suppose there is a current passing like this. So in the coil, the current is passing like this. I fold this coil like this. So it becomes two semicircular rings now. Two semicircular rings. This was of radius r, and each is now half ring of radius r. Now just imagine, how will the current flow? I can just imagine like this, and then like this, it will go like this. That's how the current is going. I place this system of two half rings something like this. If I place it something like this, then this part I call it part 1, and this part I call it part 2. So this is part 1 and this is part 2. The part 1 lies in the YZ plane, and the part 2 lies in the XZ plane. The area of each, I can say now, this current carrying coil, so both are two magnetic dipoles. For the first dipole, look at that, the magnetic field is here, that is minus I cap. And for the second, look at that, the current is clockwise like this, so downward, minus J cap. Because what is my coordinate system? This is X, this is Y, and towards U, this is Z. Indian Airlines. So magnetic dipole moment for one, I pi r square by 2, vector wise minus I cap plus I pi r square by 2 area, direction minus J cap. So easy. Once you picturize, look, the beautiful problem, it has now become so easy. So this is equal to minus pi r square by 2 I cap minus pi r square by 2 I J cap. So what is the magnitude of the magnetic moment of these two, sum total of that, the vector sum, magnitude, this will be root 2 times the magnetic moment of one of them, that is pi r square by 2 into I. So M is root 2 times pi r square. So if I want to break this root 2, so root 2 will come here, the answer would be pi r square by root 2 into I, pi r square by root 2 into I. Direction, well, there was one vector like this for the first dipole and for the second dipole like this. So M arrow, I can say, lies in the minus x minus y plane, and both the compos are equal, so magnetic moment will be exactly like this, making 45 degrees. So M arrow will be making 45 degrees like this with the minus x axis. Beautiful picturization, and by the use of vectors, so easily you have understood this problem. Let me now take you to a second problem. The second problem is something like this. Now you think of the mithai jalebi. It's something like this. The halwai does this. Look at that. Now of course he does this, but I am doing like this. So there is a current. Just follow my hand. The current is flowing like this. Spiral in the xy plane, spiraling in the xy plane. Total number of turns is n. The inner radius is r1. The inner radius is r1, and then it goes on increasing. All these are insulated turns, they don't touch each other, and the current in each turn is I. The current in each turn is I. Okay? So you follow the system? Right. Total number of turns are n. So turns per unit length. Turns per unit length will be n upon r2 minus r1. This will be turns per unit length, and if I take thickness x. Now what I am doing is, look at this blue shade. I am taking the inner radius x and the outer radius x plus dx. So within this dx, the number of turns are dn. So dn will be number of turns divided by r2 minus r1, where the total number of turns are over a distance r2 minus r1 multiplied by dx. Right. I find the elemental dipole moment dm of this blue area, that will be pi x square area multiplied by I multiplied by dn, that is the number of turns within this blue shaded thing, that is between x and x plus dx. So dn, I just replace. So this will be pi x square I n dx upon r2 minus r1. Then the total magnetic moment, integral of this, constants I take out, pi n I upon r2 minus r1, x square dx, simple integral, x square dx, x cube by 3, limits of integration r1 to r2. Finish, the job is done. So that dipole moment of this system is pi n I upon 3, I take 3 out, r2 minus r1 into r2 cube minus r1 cube. Of course, the direction of M arrow, if the current was going like this, look at that, you are seeing it as clockwise. So here, inside the board, that is minus k cap. So M, the direction of M arrow magnitude is this, and the direction is along minus k cap, along minus z. I hope you have enjoyed my video and understood your concept of the dipole moment, and with these problems you have consolidated your understanding. Thank you.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.